Hey Internet, so if you're in the field of data science or big data, you may have heard some buzz about Elasticsearch, and you might be wondering, how does a search engine technology help me in extracting meaning from my data at scale? Well, it turns out that for some problems, Elasticsearch can give you an answer back in milliseconds when other systems like Hadoop or Apache Spark might take hours. So let's dive in together, and you'll end up with a very powerful new tool in your big data arsenal. Let's start off with sort of a 30,000-foot view of the Elastic Stack and the components within it and how they fit together. So Elasticsearch is just one piece of this system. It started off as basically a scalable version of the Lucene open source search framework, and it just added the ability to horizontally scale Lucene indices. So we'll talk about shards of Elasticsearch, and each shard in Elasticsearch is just a single Lucene inverted index of documents. So every shard is an actual Lucene instance of its own. However, Elasticsearch has evolved to be much more than just Lucene spread out across a cluster. It can be used for much more than full text search now, and it can actually handle structured data and aggregate data very quickly. So it's not just for search, it can handle structured data of any type. And you'll see it's often used for things like aggregating logs and things like that. And what's really cool is that it's often a much faster solution than things like Hadoop or Spark or Flink. They're actually building in new things into the Elasticsearch all the time with things like graph visualization and machine learning that actually make Elasticsearch a competitor for things like Hadoop and Spark and Flink, only it can give you an answer in milliseconds instead of in hours. So for the right sorts of use cases, Elasticsearch can be a very powerful tool and not just for search. So let's zoom in and see what Elasticsearch is really about. At a low level, it's really just about handling JSON requests. So we're not talking about pretty UIs or graphical interfaces when we're just talking about Elasticsearch itself. We're talking about a server that can process JSON requests and give you back JSON data. And it's up to you to actually do something useful with that. So for example, we're using curl here to actually issue a REST request with a get verb for a given index called tags, and we're just searching everything that's in it, and you can see how the results come back in JSON format here, and it's up to you to parse all this. So for example, we did get one result here called for the movie Swimming to Cambodia, which has a given user ID and a tag of Cambodia. So if this is part of a tags index that we're searching, this is what a result might actually look like. So just to make it real, that's a sort of output you can expect from Elasticsearch itself. But there's more to it than just Elasticsearch. There's also Kibana, which sits on top of Elasticsearch, and that's what gives you a pretty web UI. So if you're not building your own application on top of Elasticsearch or your own web application, Kibana can be used just for searching and visualizing what's in your search index graphically. And it can do very complex aggregations of data, it can graph your data, it can create charts, and it's often used to do things like log analysis. So if you're familiar with things like Google Analytics, the combination of Elasticsearch and Kibana can be used as sort of a way to roll your own Google Analytics at a very large scale. Let's zoom in and take a look at what it might look like. So here's an actual screenshot from Kibana looking at some real log data, and you can see there's multiple dashboards you can actually look at that are built into Kibana, and this lets you visualize things like where are the hits on my website coming from, and what are the error response codes, and how are they all broken down, and what's my distribution of URLs, whatever you can dream up. So there are a lot of specialized dashboards for certain kinds of data, and it kind of brings home the point that Elasticsearch is not just for searching text anymore. You can actually use it for aggregating things like Apache access logs, which is what this view in Kibana does. But you can also use Kibana for pretty much anything else you want too. Later on in this course, we'll use it to visualize the complete works of William Shakespeare, for example. And you can see how it can also be used for text data as well. It's a very flexible tool and a very powerful UI. We can also have something called Logstash and the Beats framework, and these are ways of actually publishing data into Elasticsearch in real time in a streaming format. So if you have, for example, a collection of web server logs coming in that you just want to feed into your search index over time automatically, Filebeat can just sit on your web servers and look for new log files and parse them out, structure them in the way that Elasticsearch wants, and then feed them into your Elasticsearch cluster as they come in. Logstash does much the same thing. It can also be used to push data around between your servers and Elasticsearch, but often it's used as sort of an intermediate step. So you have a very lightweight Filebeat client that would sit on your web servers. Logstash would accept those and sort of collect them and pull them up for feeding into Elasticsearch over time. But it's not just made for log files, and it's not just made for Elasticsearch and web servers either. These are all very general purpose systems that allow you to tie different systems together and publish data to wherever it needs to go, which might be Elasticsearch, might be something else, but it's all part of the Elastic Stack still. But it can also collect data from things like Amazon S3 or Kafka or pretty much anything else you can imagine, databases, and we'll look at all of those examples later in this course. Finally, another piece of the Elastic Stack is called XPack. This is actually a paid add-on offered by Elastic.co, and it offers things like security and alerting and monitoring and reporting features like that. It also contains some of the more advanced features that are just starting to make it into Elasticsearch now, such as machine learning and graph exploration. So you can see that with XPack, Elasticsearch starts to become a real competitor for much more complex and heavyweight systems like Flink and Spark. But that's another piece of the Elastic stack when we talk about this larger ecosystem. And you can see here that there are free parts of XPack, like the monitoring framework, that let you quickly visualize what's going on with your cluster. What's my CPU utilization, system load, how much memory do I have available, things like that. So when things start to go wrong with your cluster, this is a very useful tool to have for understanding the health of your cluster. So that's it at a high level, the Elastic stack. Obviously Elasticsearch can still be used for powering search on a website, like Wikipedia or something, but with these components, it can be used for so much more. It's actually a larger framework for publishing data from any source you can imagine and visualizing it as well through things like Kibana. And it also has operational capabilities through XPack. So that is the Elastic stack at a high level. Let's dive in more into Elasticsearch itself and learn more about how it works. So before we start playing with our shiny new Elasticsearch server, let's go over some basics of Elasticsearch first so we understand the concepts of how it works, what it's all about, how it's architected, and when we're done with that, we'll have a quick little quiz to reinforce what you learned. After that, we'll start messing around with it. So there are three main logical concepts behind Elasticsearch. The first is the document. So if you're used to thinking of things in terms of databases, a document is a lot like a row in a database. It represents a given entity, something that you're searching for. And remember, in Elasticsearch, it's not just about text. Any structured data can work. Now, Elasticsearch works on top of JSON formatted data. If you're not familiar with JSON, it's basically just a way of encoding structured data that may contain strings or numbers or dates or what have you in a way that you can actually transmit it across the web cleanly. And you'll see a ton of examples of this throughout the course, so it'll make more sense later on. Now, every document can have a unique ID, and you can either explicitly assign a unique ID to it yourself or allow Elasticsearch to assign it for you. And it also has a given data type that describes what sort of thing this document is. So for example, you might have documents that represent encyclopedia articles or documents that represent log entries from your web server. And that's where the concept of types comes in. So you can have many documents that belong to a given type. And a type is basically a schema or a mapping shared by a bunch of documents. So for example, you might have a type that defines what an Apache access log entry looks like. And that might define a mapping that says an Apache access log contains things like a request URL and a status code and a request time and a referring URL and things like that. Or you might have a type that represents an encyclopedia article, for example, that represents things like the text of the article itself, the author of the article, the date the article was written, whatever else there might be, the title of the article. So you can think of a type as a schema. And again, if you take this back to a database analogy, it's a lot like a table, where you define the individual columns that are in a given row or a document in our terminology. Finally, there's the concept of an index, which is a collection of types, and it is basically an entity that you can search across. So if you need to search across multiple different types potentially, then you'd want to make sure that all those types are contained within the same search index. So an index is sort of the highest level entity that you can query against in Elasticsearch. And it can contain a collection of types, which in turn contain a collection of documents. So again, bringing this back to an analogy of a database, you can think of an index as a database, a type as a table, and a document as a row. Those are kind of the analogies there of database to Elasticsearch world. Now, of course, it's not quite that simple. Basically, what is an index? Well, an index is actually what's called an inverted index, and this is basically the mechanism by which pretty much all search engines work. So the idea is that if I have a couple of documents, let's assume they just contain text data here. Let's say I have one document that contains Space, the Final Frontier, these are the voyages. And maybe I have another document that says, he's bad, he's number one, he's a space cowboy with a laser gun. And if you understand what both of those are references to, then you and I have a lot in common. Now, an inverted index wouldn't store those strings directly. Instead, it flips it on its head. So what it does in a search engine is it actually splits each document up into its individual search terms. And in this example, we'll just split it up for each word, and we'll lowercase them just to normalize things. And then what it does is it maps each search term to the documents that those search terms occur within. Okay, so in this example, the word space actually occurs in both documents. So my inverted index would indicate that the word space occurs in both documents 1 and 2. The word the also appears in both documents, so that will also map to both documents 1 and 2. And the word final only appears in the first document. So our inverted index would map the word final, the search term final, to document 1. Now, it's a little bit more complicated than that in practice, and in reality, it actually stores not only what document it's in, but also the position within the document that it's in, so we can do things like phrase search and stuff like that. But at a high conceptual level, this is the basic idea. An inverted index is what you're actually getting with a search index, where it's mapping things that you're searching for to the documents that those things live within. And of course, it's even not quite that simple. So how do I actually deal with the concept of relevance? Let's take, for example, the word the. How do I deal with that? So the word the is going to be a very common word in every single document. So how do I make sure that only documents where the is like a special word are the ones that I get back if I actually search for the term the? Well, that's where TF-IDF comes in. That stands for term frequency times inverse document frequency. It's a very fancy sounding term, but it's actually a very simple concept. So let's break it down. Term frequency is just how often a given search term appears within a given document. So if the word space occurs very frequently in a given document, it would have a high term frequency. Or if the word the appears frequently in a document, it would also have a very high term frequency. Now, document frequency is just how often a term appears in all of the documents in your entire index. So here's where things get interesting. So the word space probably doesn't occur very often across the entire index, so it would have a low document frequency. However, the word the does appear in all documents very frequently, so it would have a very high document frequency. So when we divide term frequency by document frequency, and that's the same as multiplying by the inverse document frequency mathematically, we get a measure of relevance. So we see how special is this term to this document. It measures not only how often does this term occur within this document, but how does that compare to how often this term occurs in documents across the entire index. So with that example, the word space in an article about space would rank very highly. However, the word the wouldn't necessarily rank very highly if that's a common term found in every other document as well. And this is the basic idea of how search engines work. If you're searching for a given term, it will try to give you back results in the order of their relevancy, where relevancy is loosely based at least on the concept of TF-IDF. Got it? It's really not that complicated. So how do you actually use an index in Elasticsearch? Well, there's three ways we can talk about. One is the RESTful API. Now, if you're not familiar with the concept of REST queries, let me explain it at a very high level. It's just like how you request a web page from a web server from your web browser on your desktop. So when you're requesting a web page on your browser, like from Chrome or whatever you use, what's happening is that your browser is sending a REST request to a web server somewhere. And every REST request has a verb, like get or put or post, and some sort of body that specifies what it is that you want to get back. So for example, if you're looking for a web page, you would send a REST query for a get verb, and then that get would request a specific URL that you want to retrieve from that web server. Now, Elasticsearch works exactly the same way over the same HTTP protocol that web servers work across. So, this makes it very easy to talk to from different systems. So for example, if you were searching for something on Elasticsearch, you would issue a GET request through a REST API over HTTP, and the body of that GET request would contain the information about what it is you want to retrieve in JSON format. And we'll see examples of this later on. But the beautiful thing about this is that if you have a language or an API or a tool or an environment that can handle HTTP requests, like just talking to the web normally, then it can handle Elasticsearch. You don't need anything beyond that. If you understand how to structure the JSON requests for Elasticsearch, then any language that can talk to HTTP can talk to Elasticsearch. And most of this course is going to focus on doing it that way, just so you understand how things work at a lower level and what Elasticsearch is capable of under the hood. But you don't always have to do it the hard way. If you are accessing Elasticsearch from some application that you're writing, like a web server or a web application or whatever it is, often there will be client APIs that provide a level of abstraction on top of those REST queries. So instead of trying to figure out how do I construct the right JSON format for the type of search that I want or inserting the kind of data that I want, there's a lot of client APIs out there that make it easier for you and just have specialized APIs for searching for things and putting things into the index without getting into the nitty-gritty of constructing the actual request itself. So whether you're using Python or Ruby or Perl or C++ or Java, there are APIs out there that you can just use. Finally, there are even higher level tools that can be used for analytics, and one that we'll look at in this course is called Kibana. It's part of the larger Elastic stack. And that is a web-based graphical UI that allows you to interact with your indices and explore them without writing any code at all. So it's really more of a visual analysis tool that you can unleash upon pretty much anyone in your organization. So in order of low-level to higher-level APIs, there are RESTful queries that you can issue from whatever language you want. You can use client APIs that make things a little bit easier, or you can just use web-based UIs to get the information you need as well. So those are the basic concepts of how Elasticsearch is structured and how you interface with it. With that under our belt, we can talk more about how it works under the hood and how its architecture works. Let's talk about Elasticsearch's architecture and how it actually scales itself out to run on an entire cluster of computers that you can scale up as needed. So the main trick is that an index in Elasticsearch is split into what we call shards, and every shard is basically a self-contained instance of Lucene in and of itself. So the idea is that if you have a cluster of computers, you can spread these shards out across multiple different machines. And as you need more capacity, you can just throw more machines into your cluster and add more shards to that entire index so that it can spread that load out more efficiently. So the way it works is once you actually talk to a given server on your cluster for Elasticsearch, once it figures out what document you're actually interested in, it can hash that to a particular shard ID. So we'll have some mathematical function that can very quickly figure out which shard owns a given document, and then it can redirect you to the appropriate shard on your cluster very quickly. So that's the basic idea. We just distribute our index among very many different shards, and a different shard can live on different computers within your cluster. Let's talk about the concept of primary and replica shards. This is how Elasticsearch maintains resiliency to failure. One of the big problems that you have when you have a cluster of computers is that those computers can fail sometimes. You need to deal with that. So let's look at this example. We have an index that has 2 primary shards and 2 replicas. So in this example, we're going to have 3 nodes, and a node is basically an installation of Elasticsearch. Usually, you'll see 1 node installed per physical server in your cluster. You can actually do more than one if you want to, but that would be a little bit unusual to do. But the design is such that if any given node in your cluster goes down, you won't even see it as an end user. You can handle that failure. So let's take a close look at what's going on here. In this example, I have 2 primary shards. That means those are basically the primary copies of my index data. And that's where write requests are going to be routed to initially. That data will then be replicated to the replica shards, which can also handle read requests whenever we want to. So let's take a look at how this is set up. Elasticsearch figures this all out for you automatically. It's kind of like what Elasticsearch gives you. So if I say I want an index with 2 primaries and 2 replicas, it's going to set things up like this if you give it 3 different nodes. So let's look at an example here. Let's say that node 1 were to fail for some reason. It had some disk failure, the power supply burned out, who knows, could be anything. So in this case, we're going to lose primary shard 1 and replica shard 0, but it's not a big deal because we have a replica of shard 1 sitting on node 2 and another replica sitting on node 3. So what would happen if node 1 just suddenly went away is Elasticsearch would figure that out, and it would elect one of the replica nodes on 2 or 3 to be the new primary. And, since we have those replicas sitting there, it's fine. We can keep on accepting new data and we can keep on servicing read requests because we're now down to 1 primary and 1 replica. And that should be able to get us by until we can restore that capacity that we lost with node number 1. Similarly, let's say, node number 3 goes away. In that example, we lost our primary node 0, but it's okay because we had a replica sitting on node 1 and node 2. And Elasticsearch can just basically promote one of those replicas to be the new primary, and it can get by until we can restore the capacity that we lost. So you can see, using a scheme like this, we can have a very fault-tolerant system. In fact, we could lose multiple nodes. Node 2 is just serving replica nodes at this point, so we could, in fact, even tolerate node 1 and node 2 going away at the same time, in which case we'd be left with a primary all on node 3 for both of the shards that we care about. So it's pretty clever how that works. There are some things to note here. First of all, it's a good idea to have an odd number of nodes for this sort of resiliency that we're talking about, but it's pretty cool, right? And the idea is that you would just round robin your requests as an application among all the different nodes in your cluster. It would spread out the load of that initial traffic. Let's talk a little bit more about what exactly happens when you write new data or read data from your cluster. So let's say you're indexing a new document into Elasticsearch. That's going to be a write request. Now, when you do that, whatever node you talk to will say, okay, here's where the primary shard lives for this document you're trying to index. I'm going to redirect you to where that primary shard lives. Okay? So you'll go write that data, index it into the primary shard on whatever node that lives on, and then that will automatically get replicated to any replicas for that shard. Now, when you read, that's a little bit quicker. It can just route it to the primary shard or to any replica of that shard. Okay, so that can spread out the load of reads even more efficiently. So the more replicas you have, you're actually increasing your read capacity for the entire cluster. It's only the write capacity that's going to be bottlenecked by the number of primary shards you have. Now, this kind of sucky thing is that you cannot change the number of primary shards in your cluster later on. You need to define that right when you're creating your index up front. And here, by the way, is what the syntax for that would look like through a REST request. We would specify a put verb on our REST request with the index name, followed by a setting structure in JSON that defines the number of primary shards and the number of replicas. Okay. Now, this isn't as bad as it sounds because a lot of applications of Elasticsearch are very read heavy. If you're actually powering a search index on a big website like Wikipedia or something like that, you're going to get a lot more read requests from the world than you're going to have indexes for new documents. So it's not quite as bad as it sounds in a lot of applications. Oftentimes you can just add more replicas to your cluster later on to add more read capacity. It's adding more write capacity that gets a little bit hairy. Now, it's not the end of the world if you do need to add more write capacity. You can always re-index your data into a new index and copy it over if you need to, but you want to plan ahead and make sure you have enough primary shards up front to handle any growth that you might reasonably expect in the near future. We'll talk about how to plan for that more toward the end of the course. By the way, just as a refresher, let's also talk about what actually goes on with this particular put request for defining the number of shards. So in this example, we're saying we want 3 primary shards and 1 replica. How many shards do we actually end up with here? Well, the answer is actually 6. So we're saying we want 3 primary shards and 1 replica of each of those primary shards. So you see how that adds up. We have 3 times 1 is 3, plus the 3 original primaries gives us 6. If we had 2 replicas, we would end up with 9 total shards, right? 3 primaries and then a total of 6 replicas to give us 2 replica shards for each primary shard. So that's how that math works out there. It can be a little bit confusing sometimes, but that's the idea. But anyway, that's the general idea of how Elasticsearch scales and how its architecture works. Important concepts here are primary and replica shards and how Elasticsearch will automatically distribute those shards across different nodes that live on different servers in your cluster to provide resiliency against failure of any given node. It's pretty cool stuff. All right, like they like to say in my kids' schools, it's time to show what you know. It's quiz time. Don't worry, not too hard. Just want to make sure you were awake during these past few lectures. First question. The schema for your documents, that is the definition of what sort of information is stored within your document, is defined by what? The index, the type, or the document itself? Where is the information stored as to the actual schema of the information that a document contains? The answer is the type. So the type is basically, again, the equivalent of a table in a database. It defines the individual fields and what data types they are that a document contains. So again, going back to the example of an Apache log entry, that type might define things like the URL that was requested, or the status code, and the request time, and the referring URL, and things like that. Or if we're storing something like Wikipedia entries, it might just include things like the text of the article itself, the author of the article, the title of the article, things like that. That is all defined by the type of a document. And again, we define types in Elasticsearch by defining what's called a mapping when we're setting up our indexes. Question 2. What purpose do inverted indices serve in a search engine? This isn't just specific to Elasticsearch, it's in general for search engines. Does an inverted index allow you to search phrases in reverse order? Do they quickly map search terms to the documents that they reside within? Or are they a load balancing mechanism for balancing search requests across your entire cluster? What do you think the answer is? If you said the second one, you're right. They quickly map search terms to documents. So remember, an inverted index simply maps out specific search query terms to the documents that they live in. So as you index documents, an inverted index is actually created where it splits those documents into search terms and has a very quick lookup of where to find those search terms in given documents. Next question. If I have an index configured for 5 primary shards and 3 replicas, how many shards would I have in total? A little bit tricky here. Think about that for a little bit. Is the answer 8, 15, or 20? I can think of ways of doing the math where I could get any of those answers, but the correct answer is, hit pause if you still have to think about it. No cheating. The answer is 20 shards. So the way that works is that I have 5 primary shards, so I start with 5 shards, and then I want 3 replicas of each shard as well. So 3 times 5 is 15. So I end up with 5 primaries and 15 replica shards for a total of 20 shards in this particular example. Remember how that works because they can add up fast. And remember, a given node can actually contain many different shards. So, it will distribute shards among nodes in whatever way makes sense on your cluster automatically. Just because I have 20 shards does not mean I need to have 20 machines in my cluster. We can have many shards on a given node. Next question. Elasticsearch is built only for full text search of documents. True or false? Well, you got a 50-50 shot on this one, but if you've been paying attention at all, you know the answer is false. Elasticsearch can index any sort of structured data with any kind of mapping you can dream up. So it's not just for full text search anymore. It's not just for searching encyclopedias and websites and blogs. It can also be used for searching and even aggregating and visualizing numerical data or time-based data or whatever you can dream up. And increasingly it's being used as a tool, for example, for aggregating weblogs from web servers and sort of building a system that can compete with Google Analytics and things like that. So Elasticsearch is not just for search anymore. Hey, I hope you enjoyed this video and maybe learned a thing or three. If you'd like to learn more with me, please check out the link in the description below. I have a whole larger course on data science, deep learning, and machine learning with Python there. It's very popular and highly rated, so I hope you'll check it out. And you'll also get a really nice discount on it by using that link in the description there. Anyway, thanks for watching, and I hope to see you again soon.